All right, as we begin, we're going to start with some definitions. We're going to be um, looking at parametric equations. And what we want to do is we want to set a way of defining these. And yes, these are going to be the definitions that are in your book. Um, what we're hoping to do here is really get our definitions in place so that we can work with things that functional calculus we're not able to work with. Specifically, vertical line tests being failed, some more complex curves, and how they relate to real life situations. So, our definition will be if x and y are given as functions. When your book gives your functions y, x and y, I'll say x is some function of t, and y is some other function of t. And I think I would say are given some functions of a parameter t. I would introduce the other parts of the definition right here. That x and y are given as functions where the independent variable is some parameter t. And so it's going to be given over an interval I of t values. Then the set of points which are defined by the functions defined by these equations is a parametric curve. And the equations are called parametric equations. Our job has been to introduce another variable, another independent variable that has its own domain, and that domain will define the relationship. And that relationship comes out as a set of points, right? We're now getting a set of points that define a curve. We are still in the xy plane as we have been with other functions. It's just we're bypassing the vertical line restrictions that we had by using a parameter for it. And so your book will go on to note the variable t is a parameter, and that its domain I is the parameter interval, you'll notice the book uses t. When this notation and these concepts were explored, people were looking at dynamical systems and the calculus of moving bodies and fluids and fields. So they're looking for things, how things evolved in time. And so we're getting t for time, though as a mathematical entity, these things exist within their own geometries and their own definitions. If I is a closed interval, then you have a well-defined initial point, which is when x is at f of a and when y is at g of a. And a terminal point, which is when f is at, or when x is at f of b and y is at g of b. And when all this happens, we say that what maps out of this is a parameterized curve, and everything is a parameterization of the curve. So we'll use the word parameter in its noun, its adjective, and verb sense, so to speak. Let's look at an example. I'm going to do the first example in the book, and then we'll look at a couple others. I think I'll do the first 3 examples in the book, and then we'll dig it a little bit deeper into these. I'll try to cut these videos down into sections, but to make our definition have meaning, let's look at example 1. We will have a parameterized curve where x is equal to the sine of pi over 2 times t, y is equal to t, and t is on the closed interval between 0 and 6 inclusively. A good way to work at this, as we've done whenever introduced to new functions or even introduced to functional concepts, is to make a table of values. So let me just make a table here. For x and y, and so t, I think I'll go by halves. And so we can really plug and chug at this point. If I drop 0 into x, 0 times pi over 2 is 0, and the sine of 0 is 0. If I put 1/2 in, I get pi over 4, and so the sine of pi over 4 is root 2 over 2. If I put 1 in, I get pi over 2, and the sine of pi over 2 is 1. And I notice I'm going to continue around my unit circle, moving by pi over 4 intervals. So I'll fill in my values as I work my way across here. And just double check, make sure 6 times pi over 2 is 3 pi, which is 0. Okay. And then in y, nicely for me, just regurgitated the t values. So I'll copy those over here. And I guess I'll want to graph this. This is always the hardest part. Get myself an x and y graph. I notice that x will never be bigger than 1, and all my y values are positive. So let's see here. I'll make that about a half, that about 1. No, it's a little too wide. Let's make that about a half. That about 1, negative 1/2, negative 1, so up a half, up 1, 3/2, 2, 5/2, 3, 7/2, 4, 9/2, 5, 11/2, 6. And we'll plot our points. So at x equals 0, y equals 0, at x equals root 2 over 2, when y is a half. Root 2 over 2 is about 0.7, so about there-ish. And then 1, then back. And we look at our parameterization and we get something akin to this. Let's see if I get all my t values. So there's 1, 2, 3, 4, 5. So that's 6. Yeah, I thought I was getting near the end. And there's 6. So make each value come through. And if I play connect the dots, because I liked all my little coloring books in kindergarten, preparing me for my mathematical career. Oops, that deleted too far back. Curve this way. And we have our typical sine graph, but it's reflected and kind of rotated because of our change in axes, because of this parameter t. A thing to note is as t increases, we move in this direction along our graph. And the interval is only between those 2 points. And so we have something that if this was our data, we're looking for a functional form of this, and we were failing our vertical line test, but a parameterization puts it into a form that we're able to manipulate and graph. All right, I'm going to plop this one up. I'm going to do my lectures in small chunks here. I'm going to look at example 2 and 3 in the book next. And then we'll look at some different examples with things like cycloids and other kind of popular curves that have been parameterized.